Thanks for coming to our talk, everybody. Let's get started. My name is Jerry. I've been a software engineer here at Red Hat for the last 6 years or so. With me today is my teammate, Zach.
Hi, my name is Zack Zlotnik. I've been at Red Hat since 2022, I think, give or take. Time sure flies these days, doesn't it?
Indeed. And welcome to our talk today, where we're going to talk to you a little bit about developing Kubernetes operators. So let's just take a quick look at what we'll cover today. We'll talk a little bit about what a development loop is and why it's important for a developer's day-to-day. We'll give you a little bit of overview about the Kubernetes ecosystem, as well as the component that Zach and I work on, the machine config operator. Right? We'll talk about our day-to-day challenges. We'll talk about how we sped up that development loop. And then one of our key takeaways is how we can make incremental improvements to our developer processes to make our lives easier. Just a quick show of hands out of curiosity. Who here works in the Kubernetes space or has even just developed an application for Kubernetes? Okay, so about half the room. So for those of you who had just raised your hands, you're in the right place. Hopefully we'll share our experiences. You can talk to us a little bit about your experiences and see how we can make this better for everybody. And for everybody else, we'll talk a little bit about general developer practices. So hopefully you'll get to take away something as well. Okay, so we'll start off by defining the development loop. There's a lot of different ways people define this, but generally think of this as your developer's day-to-day, right? You add a new feature or you fix a bug, right? And then you want to build that, right? For a web application, maybe all you need to do is update the JavaScript and you do a refresh. But for your local development, maybe you have to run a compiler and then you get a binary and then you run that locally, right? And then you would like to verify whether your changes take effect. And for a lot of developers, this will be very basic, right? This is basically your day-to-day. And maybe you don't really think of it as much in that sense, but this is sort of the most central part of what a developer's journey is, right? And why is it so important, right? And XKCD definitely says it all, is that your compilement could take a long time. And that developer loop, depending on how many times you can sort of go through it and execute and make your changes and see it run, could definitely affect your developer experience a lot, right? I'm sure many of us have been sitting there waiting for something to run just to see, oh, is it going to make that final cut by the end of today? It's I really need this to work, and it's not working, and it takes me another 5 minutes to just try it again, right? So having that developer experience be as good as it can be really helps both new and experienced programmers. So with that in mind, let's talk a little bit about what Kubernetes development looks like. So I just ripped this image off the Red Hat developer blog, and there's 1,000 better resources you can find for what a Kubernetes cluster is. But for the purposes of what we want to talk about today, we just want to sort of highlight the fact that Kubernetes is a distributed system, right? Instead of an application, you just build your local machine and you run it, or a very simple client-server architecture where you run the client in one terminal and run the server in one terminal and just ping against each other. Kubernetes is a much more distributed system. Right? You have a lot of compute resources that you can distribute out across a lot of different nodes, which are resources within the cluster. And then you kind of go through the central developer API, or the central API to do all your operations. And all of this is sort of written in Golang. And if you're not too familiar with Golang, the way I like to describe it is imagine if you were trying to re-implement C, but make it syntactically look like Python, to make it simple and lightweight. And my friend always used to tell me that he has a conspiracy theory that Kubernetes was really just an advertisement for Google's Golang. And it was a really good job at it, right? Because I think a lot of people now, just out of curiosity, who here has worked with Golang at all? Okay, about half the room, so I guess it intersects with the Kubernetes crowd. Yeah, but it's a very fast, very simple sort of language in a sense. And the core functionality, which Zach will touch on a bit later, is how that build process can be made better for you. And so now we go sort of one step up, right? We started with the application that you build a binary locally. I call this the number 2 excuse of why I don't seem to be doing anything right now is my image is building. So now we add an extra layer to this. A lot of the Kubernetes ecosystem is developed in containers. And containers are abstraction of the operating system, but it's sort of a self-bundle of all the dependencies and the application itself, right? And the idea, of course, is that once you have that container, it's very easy to distribute and very easy to run across a variety of different environments that can sort of handle this API. But there's a little bit of setup you have to do, right? You have to get your base image ready. You have to set up your packages. You have to get your build process going. And then every time you rebuild that, obviously there's a lot of improvements within the container runtime and build ecosystem that makes it not as bad as you have to do that whole thing over and over again. But it does take some time. right? So, and now we would like to go one step further and talk a bit about Kubernetes operators. So an operator, again, to use like sort of a high-level explanation of what that is imagine like you're just a human operator working on a software loop. This image from the CNCF blog, I think, is a pretty good descriptor of what this looks like. It's like you as the user are no longer managing the system directly, hopefully. You give it a declarative definition of how you want something to be done or how you want your system's end result to look like. And the operator kind of acts as an intermediary human operator that makes it happen through the API and gets your resources to where they want to be. And so the component that Zack and I work on, the machine config operator, is sort of the central part of OpenShift that allows you to manage your operating system as an operator. So if you go back to like OpenShift 3 days, or if you were to like bring up like your self-hosted cluster on AWS or GCP, and you go through their documentation, right? They'll explain to you, for example, how you can build your host operating system and AMIs, as Michael would like to correct me on. And then that sort of operating system management is done by system administrators, right? Like think of your traditional system management in a distributed system. You have a system administrator that goes in and updates packages and updates the kernel and makes sure that everything is kept to date and security problem free. In OpenShift 4, we wanted to extend that such that even if you weren't a operating system admin, you can do sort of similar things to that via the Kubernetes API, so that you can define what you would like your operating system to look like, and an operator, much like a human operator would roll that across for you across your fleet. So if you have 1,000 nodes, you don't have to worry about that, right? They'll be all homogenously upgraded in a rolling fashion. And that's sort of what Zack and I work on. And this is written in Golang, and it works in OpenShift and OKD. So if you want to try it out, you can get an OKD instance or an OpenShift local instance and give it a try. And the architecture, and I'm terrible at diagram drawing, but this is sort of like a simplified version of what the diagram looks like, right? And one thing that immediately jumps out is like, this is a fully formed system. It's not a singular instance that you can just bring up like on your local machine, right? You can't just write a simple bash script to automate like a build process and just say, I'm going to build it and I'm going to test it, right? This operator, even though we call the whole thing an operator, is really a variety of different pods, starting from an operator pod that manages then the rest of the deployment. And so to test the whole system, you must have a fully formed cluster that is able to run all of these components and is able to sort of upgrade the operating system as part of that, right? And so we sort of versioned that as part of the cluster, and like especially like the daemon I would like to call out in this like little architecture diagram. It runs on every single node, and it interfaces directly with the host operating system. So if you were to write an application container that is able to completely modify the host operating system, I'm pretty sure you'd be fired the next day. But we here actually do manage the operating system for you. And so we have a very highly privileged container that essentially mounts the root operating system, file system, and then is able to sort of do all those changes, right? And so to test stuff like that is much more involved. So to go through some of those challenges that we were talking about, alluding to at the beginning, can you run this locally? Sort of. So those individual components, you can run parts of them locally, right? At the end of the day, it's a binary built in Go running in a container. You can sort of go all the way down at various points and just say, okay, if I run this binary, can I just run it locally and see what it does? Yes. But that only is a very small fraction of its functionality, right? And we would still need most of the time an API server to tell that continuous loop to tell what it needs to do to update to the new state. And because it's one, tightly coupled with the operating system, and two, requires basically a fully formed Kubernetes API, it's not that easy to really run locally. So that was kind of out of the picture at the start. The very first way we did it when we started OpenShift 4 was obviously we started the whole sandbox cluster idea, where you as a developer can request some cloud resources, get a 10 to 12 hour running instance to test your changes and have it tear down at the end, right? So that was a pretty good way to sort of have the whole thing off the bat, right? And let me illustrate for you what that looks like from end to end. So first, you sit down at your computer, you request a cluster. That's going to take 30 to 60 minutes, especially at the early stages. Now you test the behavior to say, okay, is it broken? Okay, maybe it is. Now I would like to make a change. I make that change. I build the whole component, that whole list of components as an image. I assemble a completely new OpenShift release off my version of the operator. I push that whole thing to an image registry, and then I install a completely new cluster, another 30, 60 minutes, just to see if my changes work. And early on, our install success rates were 15 to 20%, I would like to say. So this could take one iteration of this loop could take your whole day. Your developer day is spent 6 hours of it was just waiting and hoping that your cluster would just install at all, right? So obviously that was not sustainable. So by the second loop, we sort of removed one box from the picture, basically, and we said, okay, let's just start off with a cluster, but instead of rebuilding that cluster every time, why don't we just live hot swap all the components within it? Okay, that's definitely doable, right? So I have a little quick visual based on my terrible diagram of how that looks like. So first we disable the cluster version operator, which manages all the other operators. We roll out the new operator pod image. That operator pod image then rolls out all the other pods, which can take another 5 to 10 minutes. Then it starts the actual rolling update of each of the individual nodes. Again, we're an operating system manager, right? You have to reboot and update your operating system. So one at a time for control planes and workers, just to make sure that we keep etcd quorum and your applications going. So after all of that, we got ahead of ourselves there. After all that, that was maybe 15 to 30 minutes. Better than 8 hours, yes, for sure, but still not ideal. Okay, the third version, we removed another box, is what if we just, instead of replacing all the container images, we just inject the new binary directly up to the running container image. And with a little bit of hack, that can work. So a lot of our manual tests earlier on did this. And then we sort of reduced that iteration time from 15 to maybe 5 minutes, the amount of time it takes to build and push. Now, if your network is really, really slow, it might be a little longer, but we have pretty good internet nowadays. But even then, right? I'm sort of glossing over the fact that you took the 30 to 60 minutes, at least in the first place, to get a running cluster. And so one of my excuses for why I don't seem to be doing anything is I'm just waiting for the cluster to build such that I can have an API to test all these changes. So one big question here that you might not have answered yet is okay, so everything manually just sounds like a chore. Why don't you just use CI? Why don't you just unit test, right? Why do you have to do this all by hand? So so we do have very extensive unit and CI testing here in OpenShift, which if you've ever looked at any of the OpenShift repos, you'll know by the list of failing tests. The unit tests, great, but it kind of goes back to our first problem, where each unit test can only really test a small portion of the system. This is sort of by design, right? But as your system gets more and more complex, there's much more failure modes that can happen. And when you just test individual components, it's really hard to visualize how that really looks like once you have a fully formed system. And integration tests are sort of back to the original problem. We do integration tests. One run takes about 4 hours. We go through the whole installation. We have to do all the upgrades and stuff like that. And then we have to also make sure that we're kube conformant. So then we run the kube E2Es and all that stuff. So 4 hours later, you get your result, but you might as well have done it manually at that point, right? So, to summarize, we have a couple big problems. The overhead is from creating a cluster, non-ideal. The application and image builds take a chunk of time, and each iteration requires multiple steps, all of which can fail. So how do we make that better, right? There seems to be a lot that we're almost there, but we aren't yet. So with that, I'd like to pass it to Zack to talk about some of our improvements.
Thank you, Jerry. Yeah, so, do you mind if we?
Yeah, of course.
Okay, so, how did we solve these problems? First of all, let me just say that there was no singular solution to this. But as we solve these, a bunch of themes emerge. So the first one is work smarter, not harder. If you've done the build, keep your build artifacts around. You can use them again later. We all have multi-core machines. Put all those cores to use. And then the last one is, if something is tedious, time-consuming, or whatever, it deserves to be automated away. So first we need to talk about caching and incremental builds. So Go, Podman, and Builda all have a really amazing story around incremental builds. But you need there's two prerequisites to getting that. The first one is that you need to do a full build in the first place. There's really no way around that. The second part is that you need to keep the build artifacts around after you've done the build. And for containers especially, it's very easy to accidentally invalidate the image layer cache during builds. So the first solution is use cache volumes. So by doing this, you can mount a cache volume into your container image at build time where intermediate build artifacts can be stored on disk and then retrieved later. This cache volume only lives on the host. It doesn't become part of the container itself. So there might be some things in there that might seem counterintuitive to what people know is best practice for container builds, like removing the package cache, things like that. But that's not really a problem here. So the second one is, for Go in particular, Go wants to keep all of its build artifacts around. So again, we create a cache volume for that, and then setting some environment variables, we tell Go where to put all those things. And then also for installing packages. For installing packages, we create a cache volume and we put it right where DNF expects package cache, or where DNF would cache packages normally, and we tell DNF to keep the cache around. And so by doing this, we were able to reduce our incremental build time pretty significantly, down to say 1 or 2 minutes on average. The next step is, if you have a multi-stage container file, because you know that you can actually build those stages concurrently if they don't depend on one another. So Podman and Buildah have a jobs flag that you can set. It's set to 1 by default, but you can add it. You can add as many for as many cores as you want. And so by doing this, we were able to drop down to about 30 seconds on average, which is pretty good. The next one is, sometimes you need a custom built tool. Sometimes you just need that. And so what we did here was we wrote a tool that simply, it basically builds the MCO image, it builds the MCO image, pushes it to the image registry, and prepares the sandbox cluster for you, for the image to be replaced. And then it just replaces everything. And I think that over time, at least for this XKCD, I think that as other people use the same automation, reality does approach the theory a little bit more. Solution 4: you don't always need a cube cluster to talk to. There are ways to fake it, and the 2 big ones are fake client and env test. And there's probably a couple of other ones that I'm not aware of. Fake client is exactly what it says on the box. It is a fake Kubernetes client that you can inject into your code at test time that has an in-memory data store, and basically create a config map there. That's where it persists, and at the end of the test, it just gets garbage collected. Env test, on the other hand, is a package that you can import. It brings down a real Kube API server and etcd backend that runs on your machine. You can run things in it, and then tear the whole thing down at the end. But it's a little bit more involved. So with these things, we can write more tests and we can write better tests. And so by having more and more tests, we can accelerate our development loop, because now the verification phase just becomes, did the test pass? Yes? No? And we can also, with this, identify areas where maybe we don't have good test coverage, so we know what that looks like. And then lastly, we collect numbers on how long all of our tests take to run. So here's just a really quick example. I'm sorry if you're in the back. This is basically what the test coverage analysis looks like for a very simple function. All the lines that are in green, they're being called. The lines in red, in this case, aren't. And for these, it's just a, if error does not equal nil, return error type thing. This right here is one of our test execution, or test execution results. And so you can see here, this main test here was 36 seconds, and each of its subtests was 12 seconds in length, which seems like a lot. So that brings me to the next solution, which is you can parallelize test execution in Go. Assuming that your tests don't depend on each other and the code under test also doesn't have some kind of mutable global state, you can parallelize everything. And so by doing this, we can now execute our full unit test suite in roughly 15 seconds. Solution number 6, use CI if you got it. OpenShift in particular has a pretty beastly CI system that brings up a test cluster, runs a whole bunch of tests on it, and not to mention runs a whole bunch of other checks like static analysis, security analysis, all those things. And it's completely hands-off. All the developer has to do is open a pull request. And last but not least, toolbox containers. I can't stress this one enough. You can basically package all of your development tools into a single container, and then people that are new to your team can just do, toolbox create, pull spec, and there you go. And so for our team in particular, we have these rebuilt daily with all the latest tools and everything. So all you got to do is do podman pull to get the latest one. So what does our development loop look like right now with all of this? So first is the core development loop. This is the write, run, verify loop. This takes as long as it takes to run the unit test suite. So 15 seconds, maybe 30 if you made a really big change. After you've done that, you push it to your sandbox cluster. Using the MCO builder tool, the build, push, and deploy phases are completely automated for you. That takes maybe a minute or two. The verification, you can either do manual verification, it depends on what exactly you're doing, or we also have end-to-end tests that you can run that target a specific that would target a specific flow in your sandbox cluster. And then the CI loop, unfortunately we can't really do much with this just because of the nature of bringing up a cluster and running some of those really long-running tests. But we can run multiple CI jobs that target different environments like AWS, GCP, Azure. We can run them all in parallel, and they don't, so that if each one takes an hour and a half, and you run them all in parallel, it takes what? An hour and a half, give or take. So at this point, there's just a couple of key there's a couple of key takeaways here. The first one is that any kind of investment that you can make in speeding up your development loop, making your developer experience better with tooling, infrastructure, it pays dividends over time in terms of being able to quickly resolve bugs, in terms of being able to just be more productive in general. The faster and easier it is to run that test suite, the more often the whole thing will be run, instead of just running one little thing and then finding it later when CI fails. If you can run the whole thing locally very quickly, it's just a much better experience overall. And so over time, you get more confident because you know that, all right, yeah, that code's being tested. I know it works. I don't have to worry about it. And then last but not least, if you find yourself frustrated by really slow development loops, it just takes forever to make any change, you have the power to make them faster. And really the only suggestion that I have at that point is just to do it. And that's pretty much the end. I'm going to throw our resources slide up, and we can take any questions.
We do have the slide deck uploaded to the schedule already, so if you have any things that you weren't able to check out, or including the resources slide, please do check out our PDF version. Yeah. So does anyone have any questions?
So what's the benefit of using env tests rather than maybe kind other local clusters?
So kind and env test serve two different purposes. Env test pretty much automates the setup of those two things on your machine so that you can test against it. Kind, on the other hand, I think is just if I'm not mistaken, is completely a local Kubernetes cluster that persists. Env test, on the other hand, brings it up for your test, runs your test, and then tears it down at the end.
Any more questions?
So I'm kind of curious, and I think mtest and fake client both kind of get into the realm of mocking, right?
Mm-hmm.
And I'm curious, given the way MCO is set up and the things that it does, have you ever considered testing scenarios where you would have the daemon being tested as a mock in its own like private instance, where you're like mocking the rest of the cluster, because the daemon's functionality is like updating the operating system, right? It seems like you could separate that from the Kubernetes cluster and then just like mock everything around it. Although, that might be really complicated. I'm just curious. What do you think about mocking? Is that something that you think about with the MCO?
That is.
Oh, sorry. I can take like half of that, and I'll let Zach talk about the other half. So yes, we have thought about that a lot. So one of the things is that kind of already exists today. The daemon doesn't only run on like OpenShift. Like it can run on like bare metal, like rel nodes basically, right? It has a
Or
single code
VMs.
aspect. It works on like hosted control planes and like provisioning guest pools. So within those spaces, there are tests within our test suite that test some sub-functionality of it more in an individualized instance, because it's not exactly like doing the whole thing, right? Some of it can just literally take a file and provision off of that. The test does happen in some specific instances, but you're right, it doesn't actually do that for most of our E2E testing. So with that set up,
Yeah. So I've been actually having a whole bunch of like just brain blasts about how to do that. And in fact, Ines and I actually had a really good conversation about that yesterday. So yes, it is something that is kind of top of mind, and I actually have a whole doc about it.
thanks for the question.
Yes, thanks.
Any more questions? Thank you, Jerry. Thank you, Zach.
Thank you, Mike.
Thank you.